السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. First رمضان مبارك، كل عام وانتم بخير. إن شاء الله may Allah accept all of our deeds in these days إن شاء الله. Today is the first lecture in Ramadan and also last lecture إن شاء الله. I will give you after this give you time إن شاء الله to work on the project submission. So just bear with me tonight. It's the only lecture that we will spend that time that late. Inshallah, I will try also to be as brief as possible so that we don't stay late, inshallah. Okay, last time we started to talk about BERT for ranking. So we mentioned that ranking is converted as a classification problem when we use BERT. What we will do is that we will pass the query and the sentence or the text that we want to check if it's relevant or not to BERT, and we'll get the probability that the document is relevant, which will be the score that we will use to rank the documents, and we call that relevance classification. So we discussed that last time, and we also mentioned how is that related to learning to rank. We said that this is, of course, kind of a point-wise learning to rank. And that was the setup. We first retrieve documents based on the query using traditional retrieval models like BM25. Then we take the top of them, we call them candidate documents or texts, and then we re-rank them. And by that, we eventually get the final rank list. So the focus last time and almost half of today's lecture will be on this part, which is re-ranking. So the first model that we started to discuss last time, and inshallah will continue today, is MonoBERT. Anyone can summarize what MonoBERT is doing? Anyone? I know that this lecture now is the last one and we will not be examined on that, but I think the topics are very important for your knowledge and also for your projects. So please let's discuss. Yes, Muhammad?
Sorry, I'm probably incorrect with my assumption, but if I recall this correctly, we used MoneyBERT once we got our, using, for example, BM25, for example, to retrieve our data set, and then we feed it to MoneyBERT to rank each document. That's at least how I recall it.
Do we use it to rank every document or to score every document?
Score every document.
Score every document, right? And based on the score, we rank the documents.
Or re-rank.
Sorry?
Re-rank the document.
Re-rank, exactly. We re-rank the documents based on the scores that we assign using BERT. Okay, and that's the solution called as a whole MonoBERT. And as we saw last time, we apply the model only on the documents, the top documents that we retrieved using BM25 or any initial retrieval model. So it's not, of course, done in practice. We cannot do that for every document in the collection, of course. And for that, of course, we use BERT. We give the query and the document together with a separator, and we get the embeddings, the CLS embeddings, which represent the entire input. We take this embedding and we add a fully connected layer. We use softmax. We get the probability eventually. The value of the softmax at the relevant output node will be considered the probability that this document is relevant to the query, and that will be the score that we will use to rank or re-rank the documents in the initial rank list. Don't remember if we discussed this loss function or not, but this is the loss function that is used for training MonoBERT. Of course, the training data will be the positive and negative documents, of course, with their corresponding queries. The goal is to get SJ here to be 1, because these are positive examples. So if it's 1, then the log will be 0, so the loss will be 0 from that part. And we want SJ to be 0 for the negative example. So if all of them are zeros, then again, this part would be 0, so the loss would be 0. Otherwise, the loss will be positive value, and thus we will update the model during the training phase. This is the overall picture of MonoBERT. I think this is where we stopped last time, if I remember correctly. So BM25, in the beginning, we get a list of documents, and then we apply MonoBERT. We take each document from this list associated with the query, and we give it to MonoBERT to get the score for that document. Eventually, we have a score for each document, and we get a final ranking. The results also, I think we discussed it, so good that we go through the briefly MonoBERT, because we will depend on that in the rest of the lecture. As we saw, it improved the performance over, of course, BM25, and even when we did blind relevance feedback, we also got improvement over the initial ranked list. Okay, so it is clear that it made really a significant improvement from 0.5 to 0.74 almost in NDCG. That's a very big jump, and also here from 0.52 to 0.74, that's also a big jump. I think we didn't see that last time, so that was for this one. There is a research question here, which is what is the effect of increasing the depth of the initial ranked list on the effectiveness? So if we apply MonoBERT only on the top 10, what will be the performance? If we apply it on the top 100, what will be the performance? If we apply it on the 1000, what will be the performance? So will the performance degrade as we add, as we go down the list, or it improves? It turned out that as we go down, MonoBERT was capable of bringing up the list the relevant ones. So actually the performance increases up to even 10,000. So going deep in 10,000 documents retrieved by BM25, MonoBERT was able to improve the performance even at 10,000. After 10,000, it seems like there's no much gain after that between 10,000 and 50,000. But it is really interesting to see that up to 10,000 there was an improvement. We wouldn't expect that clearly. Maybe the adding of so many non-relevant documents will be really hard for MonoBERT to really get or assign scores high to the other documents, but it was able to really do a good job in capturing the relevant documents as much as it can. Another research question that the authors of MonoBERT try to address, which is how useful is BM25 signal? So MonoBERT so far in the discussion that we had ignores completely the BM25 score. So it uses BM25 to retrieve a list of documents, but then we completely ignore BM25 scores and we assign new scores to every document using the BERT model. Here, the authors try to do some interpolation between the BM25 score, which is this one, and the BERT score, which is MonoBERT score. Okay, so they made a linear combination between the BM25 score and the BERT score, and to do that they normalized the BM25 scores across the entire list of documents for the same query, so that the scores can be comparable, because you know BM25 scores are not between 0 and 1. So by this normalization, it will be between 0 and 1. Now we can interpolate, or we can make a linear interpolation between the BM25 score and BERT score, and that score now will be a score between 0 and 1. Right. The question here is, how useful is that? Can we find, of course, this interpolation is controlled by the parameter alpha. Okay, so if alpha is 0.1, then 0.1 of the score will be coming from the BM25 score, which is the first stage, and 90% of the score will come from mono-BERT score. So they changed the value of alpha to see if there is any value of alpha that will give us better ranking at the end, and here is the answer. So on the x-axis we will find alpha, and on the y-axis we'll find the performance measure, which is mean reciprocal rank at 10 in this experiment. So looking at this figure, what is the answer to the question? What do you think?
When alpha is 0 is the best?
It seems so.
So when it completely depends on BERT.
Yes. So that's what the figure tells us, that the best performance was when alpha was 0, which means that we cancel completely, or we ignore completely, the BM25 score. Type, what is the conclusion then, Marina, I think?
The conclusion, so it's the score from BM25 has no effect on the rank. So
exactly.
Depending on BERT alone is enough.
Yes, exactly. Okay, so adding any involvement of the BM25 score was not useful at all. Okay, in this experiment, in this test collection, actually, I think in the I don't remember which one. I think was Birch. I think the one that we will discuss next. They tried it on a different test collection, and the result was different. Okay, but at least for this experiment, it was not useful. So that was the answer to the second research question. Now, as we mentioned last time, there is a limitation, of course, of BERT. Do you remember what was the biggest limitation?
Number of terms?
Size.
Yes,
It
size.
only takes a limited size of document.
Yes, not limited size of document, limited number. You said limited size of documents?
Limited size of terms.
Document. No, limited length of document, like it is only a passage from the document.
Yes, exactly. So that's the size of each document has to be, it cannot exceed 512 tokens. Okay, so that was a big limitation, because if I have a big document, then I will not be able to feed it completely or entirely to BERT. Okay, so that was a limitation. It cannot input entire documents if the documents exceed 512 tokens. 512 tokens, you can think of them like a passage. It's not a very long document, of course. So there are at least two questions raised from that. The first one, what do we input in that case? If I have a long document, how should I deal with it? Okay, so what will be the input in that case if I have a long document? And for training, and that's for inferencing, okay? And for inference, I have to deal with that somehow, because the input cannot exceed 512. And for training, we have already labels for complete documents, right? So what do we do with training, with the labels that we have? The labels are at the document level, okay? So what would we do with that? These are two questions that we will think about next. So next we'll talk about moving from passages that we discussed with mono-BERT to documents, to complete documents. So we need to know now how we will deal with complete documents. Okay.
Maybe we can re-index the passages itself
instead of indexing the document.
Okay, what do you mean by passages then?
يعني the passage that will be indexed, not the document. So we will have a label on the passage itself, not the document.
So you mean that we will divide the document into passages?
Yes.
And index each passage separately as a document, as a separate document.
Yes.
Okay, then we have two questions. How do you select the passages? I mean, where to stop, where to say that this is a passage? And then also, if the label of the document is relevant, should we say that every passage in the document is relevant or not? Okay, so we will discuss these two questions together. So the main idea here is to chunk, as Ahlam said, is to chunk the document into smaller passages, and we need to transfer somehow the labels. Okay, so if the document originally is relevant, of course, if the document is non-relevant, then it's straightforward to say that all the passages in that document are non-relevant, although that might not be very very accurate. Yani maybe in rare cases that one passage might be relevant to some extent to the query, but the entire document is not. But I think it is reasonable to assume that if a document is non-relevant, then all passages within that document are also non-relevant. But the problem actually is in the relevant document. If we have a relevant document, okay, is it straightforward to say that every passage in that document is also relevant? What do you think? Is it the case always that if a document is relevant, then every passage, let's assume that the passage is a paragraph.
Maybe my answer or the answer of the query will be in the first paragraph, not in the second paragraph. So the second paragraph will be not related or not relevant to my query.
Yes. So yeah. So in most cases, not every passage in the or paragraph in the document that is relevant is actually relevant to the query. Okay, maybe one or two paragraphs in the document are relevant, and thus the entire document was deemed relevant because of that. But generally, we cannot actually say that every passage is relevant. So if we said so, then this is an approximation. Okay, so that means that this, if we do that, then this of course we will do that. We need to do something like that for training, right? Because BERT has to be trained on maximum 512 tokens. So we'll have to actually even divide the training examples, the training documents. Okay, so we'll have to say for each passage whether it's relevant or not. So if we assume that every passage coming from a relevant document is relevant, then of course this training data will be noisy. Okay, so we'll have to keep that in mind. So these are the issues that we need to think about: how to transfer the labels and also how to chunk the documents. Okay. And we just said for simplicity that that we have the paragraphs, right? But it's not very straightforward to actually divide a document into paragraphs. Sometimes it's not easy. So we will see different ways of dealing with this problem.
So taking aside a window for the document, a fixed size window, it'll be fine.
Yes,
because
that's
the paragraph.
one way. That's one way of doing it, Marina.
Okay.
That's one way that we will discuss that. Okay, but that's one way. It's not the only way. And also another issue is that if we do that, Marina, if we just use a window, which is fixed number of tokens, will the windows or will the passages be completely mutually exclusive? I mean, there will be no overlap between them, or there will be overlap. And if there is an overlap, how much? So all of these are issues that we'll have to consider. So that's in training. So this can be done in training. In inference, if I have a model now and I want to use it to re-rank documents, Then, of course, I have to do the same, where I have to chunk the documents into smaller passages, and then I have to feed each passage separately to MonoBERT or BERT in general to get a score for that passage, right? Because BERT will not be able to take the entire document. Now, instead of having just one score for the document, we will have multiple scores. So if I have 3 passages within this document, then I will have 3 scores. What should I do with these 3 scores? I have to aggregate them somehow to get a score for the document. Okay, so now we start to think about the document level, not the passage level. BERT was able to do it very well on the passage level. How can we translate that into the document level? So we have issues in training, and we have also issues in inference. Okay, and now we will study 2 or 3 strategies in that space. Each one has some design decisions in how they chunk the documents and how they aggregate the evidence, and we will see a comparison between them, inshallah. So the first approach tries to aggregate the score. So for each passage, and we'll see, of course, how the passages are defined. For each passage, it will be passed to BERT. We'll get a score, and then we aggregate these scores to get the document score. So that's what we call score aggregation. Of course, that's an overview. We'll talk about details, but that's the big picture of that type. Okay, so we'll get a score for each document, and then we will, sorry, not for each document, for each passage, and the document, of course, has multiple passages. Then we have to aggregate those scores, as you see here, to get a final document score. Okay, and here,
Doctor, how they will know? Sorry, but how they will know that those 4 or 3 passages belongs to the same document? There is labels.
Oh, no,
There is
Marina,
any label we sent?
Marina, we are talking about inference now. Okay.
Yes, this is my work. Will be at the end here. My work. The aggregation is my work. It's not.
It's
I
not
have
BERT.
to.
Yeah, you have to do it outside BERT, of course. Yes, BERT job ends by assigning a score for a given passage. Then you have to deal with the passages yourself. You know, of course, that there is a document, and you yourself chunk it into different passages. So you will pass every passage to BERT, get the score, and then aggregate those scores. Okay, there are 2. We will study two approaches. One that assumes that every sentence is a passage. So every sentence will be passed to BERT. The second defines a passage in a different way by a window, as Marina suggested. Okay, so there are 2 ways that we will discuss. One over sentence scores, and another over passage scores. Okay, so the first one, which is over sentence scores, is called BERT. So BERT solved the problem of long documents in training in a very simple way. It just trains on very small passages already, so it doesn't need to translate any labels or divide or consider the transferring the label of the document into passages, because it actually trains on very short documents. In fact, it was trained on tweets, which are, of course, very very small. So a tweet will not probably exceed, unless in rare cases, it will not exceed 512 tokens. Okay, so in training, it was completely trained on tweets, so there was no need to chunk the training documents. Okay, and the inference is done on every sentence. So it is already trained on tweets. Halas, then done. We got a model, and that's exactly like MonoBERT. Okay, but trained on tweets. Now I have a model trained. How can I use it for inference? I will, because the tweets are considered like one sentence, the BERT model assumes that we will divide any document that we have into sentences. Okay, so individual sentences. Pass every sentence to BERT, and actually it also interpolates similarly to MonoBERT in the experiment that they did that we discussed earlier. Interpolate the first stage retrieval score like BM25 with a weighted sum of the sentence scores. Okay. And the interpolation weights are tuned on the target data set. So these are like parameters, and these weights will be tuned on the target data set. Let's say that the target data set is news, so it will be tuned on the news data set, but the model itself is trained on tweets only. Okay, so that will give us the score for the individual documents. Okay, so what is in here? In here are the top scored N sentences. So what we will do is that, given a document in training, خلاص, we trained on tweets. Okay, now we are on inference. We have a document. We will divide it into sentences. Pass every sentence to BERT here, or MonoBERT. It's the module that will give us a score. BERT is the entire approach, but we will pass the sentences, every sentence, to MonoBERT, which is trained on tweets, and we will get a score. Now we will sort those and get the top N sentences. Okay. And let's say that the weights are just ones for simplicity. So I will just add the scores of the N sentences and interpolate with the BM25 score to get the score for that document. Okay. Any question about the methodology here? Is it clear?
Doctor, I have a question.
Yes.
In this setup, we trained on tweets, and we inference. We make inference on document.
Yes, and you will see the effect on. We will see the effect of that in the results.
But the document is long compared with the size of tweet.
Exactly. Right? Yes. Yes.
Is that fair? Or good or okay? Or is that okay?
Okay. Yeah. Okay. So there are two issues here, because you said fair. Fair, you mean, is it allowed to be done? Of course, it is allowed. You can train on anything and try your best, try your luck on in the inference, in testing, right? You can do that. Yes. So that's fair if that's what you mean. But there is another question, which is whether this will be effective or not. I think this is what you mean, yes. Right? We will see that. We'll see that in the next slide.
Okay.
Okay. Did I answer your question?
Yes, doctor. Thank you.
Okay. You're welcome. Any other questions? Okay. Now let's see the performance. What happens? Let me first explain what is this. The first row, so the rows here are named by numbers. Okay. So number 1, BM25 plus RMA3. This is typical BM25 plus relevance feedback. Okay. So that's the baseline, and you see here the mean average precision is 0.29. Okay, which is the lowest across all the others. Okay, so that's BM25 plus relevance feedback. Now let's see BERT or BERT here, and there are 2 dimensions of variables here. Whatever between parentheses is the training data set. Okay, so here in that block, the training data set was microblogs, which are tweets. Okay, so here the training data is tweets. Here the training data is not tweets, but passages from a collection called MS Marco. Some of you actually are using MS Marco in their projects. these are divided into passages. So these are small passages, but longer than tweets. Okay, so that's another type of training. So it is fine-tuned. Of course, we are when we say trained, we mean fine-tuning, of course, right? Because BERT is already pre-trained, and we will fine-tune it. Here we fine-tune it using tweets. Here we fine-tune it using passages, which is bigger than tweets, and of course bigger than sentences. And here we fine-tune it on passages, then fine-tune it further on tweets. Okay, so that's the setup here. Okay, so that's what is between parentheses. Then another thing is this number 1s, 2s, 3s. That means one sentence, two sentences, three sentences. So 1, 2, 3 is the number of the top sentences that we will consider. We remember that we said that the document has multiple sentences. We will score every sentence separately, and then we take the top n scored sentences. N here is 1 or 2 or 3. Okay, so these are the numbers that we have here. So in that line, for example, we fine-tune BERT on tweets, and we scored the document by the top scored one sentence. Okay, here we take the top 2 sentences. Here we take the sum of the top 3 sentences, and so on. Okay, so I think now you understand the setup. Okay, so these are, of course, different experiments that were done. Now let's look at the results. Let's look at this block first and see whether BERT in this case is better than BM25 or not. Of course, clearly it is better, whether on mean average precision or in DCG. This experiment is done on a collection called Robust 04, which is a collection of news articles. Collection of news articles, not tweets. Okay, so news articles, which is of course much longer than tweets. So what happened is that we will chunk it into sentences and pass each sentence to BERT, and of course get the score based on the setup here. Time.
Doctor, I have a question.
Let me continue this and then get back to your question, Khawla or Marina?
Khawla.
Khawla. Okay, we'll get back to you very shortly.
Okay.
So let me explain this here, that we pre-trained on tweets, and then when we do the inference, of course, we will chunk the document into sentences, because that's the assumption here. Okay, I want that to be really clear. Yes, Khawla.
Doctor, we're ranking them based on the first 3 sentences, right? In 3S.
In 3S, yes, based on the sum of the top scored 3 sentences in the document.
Yeah, Doctor, what if a document only has maybe 3 sentences that are relevant?
Then this is the top.
And the rest is all non-relevant, maybe. It only mentions the...
No, just a second. Okay, I got now your point. We will not know which ones are relevant and which ones are not. What we will get is just a score, the probability of being relevant.
Yeah.
But we don't know if they are actually relevant or not. So we'll assume that this probability score is a relevance score, and that's what we will evaluate.
But we don't have a ratio of like relevant to non-relevant sentences, or like what if the document is very long and it has 3 very relevant sentences?
Oh, very good. Okay, that's what we are trying to evaluate to see whether this idea is good or bad, Khawla. Okay, yeah. So when we have 3S, that means that we will take the top 3 sentences and we'll sum their scores, and that will be the score of the document. And by that score of the document, we do that for all documents and re-rank them. And now we will see whether this is effective, or at least more effective than BM25 or not. That's what we want to see. Okay, and what we see here in front of us is that it is actually more effective than BM25, because in BM25 here we got 0.29, here we got all of them are actually very close to each other. They are 0.34, so 5 points, okay, which is a good improvement, of course. Okay, so that means that the idea of using BERT this way is good, but not only that, it means that there is what we call cross-domain learning. Cross-domain learning, which Wathiq hinted about earlier, that we pre-train BERT on tweets and then test it on news. That was really strange, right? If you think about it, it was not standard. Usually when we want a model to work well on news, we train it on news, right? Or if we want it to work well on tweets, we train it on tweets. Here we pre-train it on tweets and test it on news, and still we got better results than the baseline, which is BM25. So that was really striking. That was very interesting to see that the model was able actually to improve the results just by being trained on tweets. Okay, but remember that we also in BERT, we assume that the input also will be sentences, and that's why probably there was a good match. Yani the input, the training was on tweets which are of the size of sentences, individual sentences, and the inference also was done on sentences, so that there was a match, although the domain itself, so there was a match in length, but the domain itself was not matched, right? The domain was tweets here and news here. But despite that, the model gave better results than BM25. We call this zero shot. Of course, I think you now understand why we call it cross-domain, because of course these are completely two different domains, tweets and news. But why do we call it zero shot? Any idea? Why do we call this zero shot cross-domain learning? Cross-domain learning, I think, is clear. Why is it zero shot? What do you mean by zero shot? Anyone knows?
Doctor, maybe because we didn't make any modification over the pre-trained model. Just
Modification? Is that
yeah.
Wathiq?
Yes, I'm.
What do you mean by modification here?
Yeah, we didn't fine-tune the model for the task of inferring on the, for example, the news article. We trained
Exactly.
on.
Exactly. The data set that we used to train, the data set that we would use for testing, we didn't touch in training at all. Okay, that's what we mean by zero shot. The model didn't see something like that before at all in training. Okay, and that's actually the main surprise here. That although we didn't fine tune on robust 04 at all, it made a good improvement without that. So that's why we call it zero shot cross-domain learning. Now let's move a bit and look at the results as a whole and see what is the effect of changing the training data, the fine-tuning data set. So here we had a tweets data set for fine-tuning. Here we have passages, and here we have passages, then tweets. Now look at the results and tell me, what do you see? Which one was more effective? Training on tweets or training on passages, which is MS Marco, or training on MS Marco, then tweets, or passages, then tweets?
It's clearly the third one, passages and tweets,
Yeah.
tweets.
Yeah. So if you, before we do that, if we look at these two only, you will see that fine-tuning on MS Marco was not effective, as effective as the tweets, right? So here we are at the level 0.3, here we are at level 0.34 in mean average precision, similar also in NDCG. And the reason that was in the survey of course, that's just a guess, that maybe the mismatch between the size of the passages here and the sentence passage. Remember that we test on sentences, right? And here we train on passages. The passage, of course, is probably will have like 4 or 5 sentences. Okay, here it was tweet, so the size of the tweet is, we can say that it is similar to the size of a sentence, but here there is a mismatch, and that might be the reason why we didn't get that improvement over the baseline. But here we fine-tune on MS Marco first, then fine-tune on tweets, then test it on sentences, and that was the best. As you see, we got improvement over even the first block. Okay, so here we reached like 0.36 in mean average precision. And if you look at,
we can redo that, the fine tuning for the same model that we have, like we fine tuned the first time and second.
Is there anything that stops us from doing that? No.
The model can, that's only.
Of course, in terms of time, yes, of course, you will need more time. But when do we actually do that? Is that offline or online?
Offline.
Offline, right? So you can spend more time in training. Maybe you need more power, more computing power to do that. But usually the fine tuning is not as expensive as training, as pre-training. Pre-training needs a lot of computing power because we have very large data sets. But for fine-tuning, it's not the case, right? Because fine-tuning, we have few labeled examples, at least much fewer in numbers than the training examples in pre-training. Okay.
In which cases we can decide how many times, or do we need a second fine-tuning or a third fine-tuning? It depends on what.
Very good question. I don't have a solid answer, and that means that it is open question. That can be a question, a research question that you answer in your study. Okay, so maybe you can try, but of course, yeah, you have to have some intuition. Okay, you can try 2 times, you can try 3 times, you can try 3 different types of documents to fine tune and see what will be the effect on that. But I don't have a solid answer for that. I don't think even the authors of BERT had an answer before they have done this experiment. That's why I want you in your projects to have some kind, of course, not exactly these research questions, but you have to have some research questions that you test in your project. I want to try this and see what will be the effect. I want to see the effect of the length. I want to see the effect of further fine-tuning. I want to see the effect of the size of the ranked list, and so on. So these are examples of research questions. Now let's look at this block only, and you forget about these blocks. And let's look at this block. We mentioned that fine-tuning on MS Marco, then fine-tuning again on tweets was the best, right? Now let's look at which number, which n value is the best. Is it 1 sentence, 2 sentences, 3 sentences? It turned out that 2 and 3 are very close, right, to each other in terms of performance. So, and the first also is not very far, right? So it seems like 1 sentence might be enough to represent the score of the document. So the top one, so the top sentence is probably good enough. Of course, 2 is a bit better. Maybe 3 is not much better than 2, but 1 seems enough. Okay, because the difference between 1 and 2 is not that significant. Okay, so that means that the top sentence in the score of the top sentence of a long document is a good representation of the relevance score of the entire document. This is a takeaway message, okay, from that experiment, that only one sentence, if it's relevant, then it represents the relevance of the document. But do we know where that sentence is? Is it always the top sentence? I mean, the first sentence in the document? Do we know where?
No.
We don't know, right? We don't know. We don't know. It might be in the beginning, it might be at the end. You have to score all documents before you select that document, right? Because we said that this is the top, so top based on the scores. Okay, any question on BERT? So we are done with BERT, which is a model that is only trained on small documents. So it solved the problem of training on long documents by just ignoring the issue and just training only on small documents. Any questions?
Yes, doctor, I have a question. Regarding the fine-tune BERT, here when we are fine-tuning the data or using tweets or MS macro, we
Yes.
are inputting the whole tweet or the whole macro as
because both are small. Yeah,
Oh.
tweets are small. MS Marco passages, small passages.
Oh, so we are not segmenting into sentences in fine-tuning phase.
Yes,
Okay.
in the fine-tuning, we are just using raw data.
Oh, okay. Okay.
Okay. Any other questions? It's getting hotter now. Or maybe I'm more excited about the about the topic. Any other questions? Okay, so let's move on. Remember that we said that we have two approaches. One to aggregate scores over sentences, and the other is to aggregate scores over passages. So now we will talk about the second approach, which is aggregating scores over over passages. Right. Here, this approach is called BERT max, P max passage, or first passage, or sum passage. Okay, so these are three variants of the same approach. The overall idea here is to chunk the document into passages, either in training or in testing. Okay, so here we will not only train on small documents. We will open the door to any size of documents, but we'll have to convert the document into overlapping passages. So we will have a fixed window size. Of course, this is a hyperparameter that has to be tuned. Fixed window size and with overlap. So overlap is defined by the stride. The stride here is the size of the overlap. Okay, so maybe I can say that I will take a window size of 100 tokens. So every 100 tokens will be a window, will be a passage, but the passages overlap with 10 tokens. So that means that the first passage will be from 1 to 100, and then the second one will be from 91 to 191 or 190. So there is an overlap of 10 tokens, and then the third will have an overlap of 10 tokens with the second, and so on. Okay, so that's what we mean by stride here. The stride is the size of the overlapping part. Okay. Of course, these are two hyperparameters, the window size and the stride size. But the idea here is to automatically chunk the document into passages. So there's no notion here of sentence or paragraph. It's just by counting, we will chunk the document into passages of fixed size, and we have fixed stride. Now, if we do that in training and in testing, of course, in training also we will translate in a straightforward way the label of the document into the passages. So if a document is relevant, all the passages out of that document will be assumed to be relevant. And then in inference, we'll have to aggregate the passage scores. We will pass the passage to BERT, get a score for each passage, and then we have to aggregate the scores. Okay. The way that we did it in BERT, we divide the document into sentences. We score every sentence, and we get the top and sum them, weighted sum. Here we have 3 variants. To get the maximum score, so we'll have to score all passages, but after that, we assume that we will assign, we get the maximum score to be the score of the document, or we get the score of the first passage to be the score of the document, or we sum all of them. These are the 3 variants. Max P means max passage, first P, first passage, or sum P, sum of the passages. These are the 3 variants of that approach. Okay. Here's a sketch of the method, similar to what we saw before. We have every passage would be input to BERT. We get its individual score. So we have here, if we have 3 passages, we have 3 scores. Then we take the max, or the first, or the sum for these 3 variants to be the document score.
Doctor, the 3 ways have the same evaluation? Like,
what do you mean by same evaluation?
Like if I got the max and I test the results.
These are 3 different models. And it's either, we are experimenting here, okay, to see which one will be the best. Whether we get the max score, or the first score, or the sum of the scores.
And now we will know the answer, which one of them will be the best.
Yes, we'll see the results. Okay. Right. Here are the results of the experiment. Here we have 3 baselines, traditional ranking models, bag of words, sequence dependency model. We didn't actually study this in that course, and learning to rank. Okay, so we have 3 baselines, and then we have the 3 variants: BERT first P, BERT max P, BERT sum P. If you remember when we talked about TREC topics, we mentioned that the topic is defined by a title, which is a very short query, and also defined by a description, which is a larger or a longer description of the query. Okay, so you can say that this is a short version of the query, and this is a longer version of the query. Now, let's look at this, ignore the description for a second, and look at the title only. So we got something like, so here the evaluation measure is the NDCG. So we got like 41 or 42 for the traditional methods. For BERT first or max or sum, we get higher. So it seems like the idea is good, is effective compared with the traditional methods. We get higher scores, and of course, it's very clear that the max, the first actually is not that effective, and that can be expected, because we cannot say that always the relevance of the document will be represented by the relevance of the first passage. So max and sum seems better, and actually in terms of numbers, the max one is a bit better than the sum. Okay, so max or sum, I think it's they are reasonably better than the first. So that's if we look at the title. If we look at the description, you will see that we have something similar. Again, the BERT models are much better than the traditional models. But for the traditional models, when we have the description, some of the models were hurt, were worse, and some are actually SDM was actually the same, it doesn't matter. And for learning to rank, it was a bit better. Here, if you look at the numbers here first, of course, they are much better than the traditional ones. And again, max P is a bit better than some, and both are better than first. Okay, and as if you compare if you compare both now, the title and the description, you will see that the BERT models have benefited from the longer query much more than the traditional methods. And you see here, the performance here using the description, which is a longer query, is better than the title, which means that BERT was able really to make use of the longer query much better than the traditional methods, because it understands the language to some extent, of course. Okay, so you see here 0.53, which is much better than, of course, than 0.47 here. 6 points difference. That's a big jump. If we are provided with longer queries. Okay, so that's the conclusion here. So we have two conclusions here. First, of course, that the BERT models are better, even using, by the way, we are using noisy training data, right? Why? Why are we using noisy training data here? Why do we call it noisy training data?
So we don't overfit?
No. We didn't say anything about overfitting here. Why is it noisy? The data itself is noisy. The training data itself is noisy.
Because we have divided the documents into chunks, and some chunks will not be relevant to the query and some will be relevant.
Yes, although we will call them all relevant if the document is relevant. Okay, so that's why the training data here is noisy. It's not about the model that we learned. It's about the data itself, because of the way that we chunk the document into passages. Some of them are actually non-relevant, even if the document as a whole is relevant. But still, we will assume that it is relevant, and the label of it in the training data will be relevant. Okay, so the idea here, or what the point here that I wanted to say here, is that although we have noisy data, but we had very good improvement over the traditional methods. Okay, so BERT was able to really benefit even from this noisy data. Right. This is the example of, just to show you the an example of the title and the description queries. Here the title is Air Traffic Controller. The description is what are working conditions and pay for US air traffic controllers. Of course, the longer query has more keywords, and thus of course if the model is really good, it will make use of these new keywords. And that happened actually also in clearly happened with BERT, happened to much smaller extent with the traditional methods. Okay, now another experiment that they did is very interesting experiment. In this experiment, they compared max-p. Now we focus on max-p because it's the best. We compared, we did compare it between title and description, right? That was the previous slide. But here we add another line, which is description keywords. What is description keywords? They removed manually from the description the stop words and the punctuation. So they keep only the keywords in the description. Okay, so that's just an experiment. They remove that manually to see what will be the effect of removing stop words. Of course, from what we studied so far in the course, we always said that stop words are useless. We should just ignore them, whether in the document or in the query. These are stop words. We should ignore them because they are useless. They wanted to test this with BERT, because really BERT had made us rethink about the concepts that we thought that they are really basic concepts in the field. We need to recheck them now, since we have a kind of semantic matching. It's not now exact match that like what we did earlier. So when they did this experiment, if you see here, This is the performance of the sequential dependency model, which is the traditional model. With removing the stop words, it was better. Okay, going from 0.4 to 0.427, it's getting better. It improved when we removed the stop words. And by the way, this is the average length of the queries now. From 14, it is now 7 after removing the stop words. What happens to max P? What happened?
It decreases.
It decreased. The performance decreased. That was a striking conclusion or striking experiment. Removing stop words from the query
It will
given
affect
to
the
BERT,
context of the.
it will affect negatively the performance, which was not expected, right? We didn't, at least we didn't use to that. We used to improving the performance when we remove the stop words, not the opposite. But seems like BERT, because BERT is trained on language, it's actually a language representation model, it needs these stop words to understand the structure and the meaning of the sentences. So removing stop words from these sentences, although the individual stop words are not very useful, but they are useful for the structure of the sentences and thus the meaning or the understanding of BERT from the sentences. Okay, so that was really important experiment that shows that even those words, they should, at least on that setup, they shouldn't be removed. They shouldn't be removed. They also tried this with the narrative. Narrative is even longer. If you look at the example here, narrative is even longer query. Narrative says what should be the relevant documents and what shouldn't be the relevant documents, or what should be the non-relevant documents. So it's much longer. As you see, they did the same thing. They removed the stop words, and again the performance dropped a bit. Of course, not too much, but it dropped. Although in SDM, the sequential dependency model, it actually improved a lot with the narrative. Yes, Muhammad, you had a question?
Yeah, I was wondering, does that mean BERT works best when not assuming the Bagford model? Because I think that's
Sorry,
the
say it
whole,
again.
like, because from my understanding, Bagford's principle is that, like, we essentially don't care much about the word structure, just the meaning or the.
Not the meaning. Okay, Muhammad.
Yeah.
If you remember, did we talk about the meaning in the ranking models before? In the traditional ranking models, we were actually matching words, right?
Yeah.
So it wasn't about the meaning, it was about matching words in the query with the words in the document.
Yeah,
and that's why stop words didn't really mean anything to us, right? Removing them, because we don't want to match actually stop words, because matching stop words was not the goal.
Yes.
Okay. Did I answer your question?
Yeah, so that means like BERT essentially works best when not assuming a Bagford model.
It seems from that experiment, yes.
Thank you.
But in your domain, you should retest that. If you think about your project, your own problem, maybe you should retest that. Okay. Any other questions?
Yes, doctor. I didn't understand why we call it noisy data, since we divide the data into sentences. Is that noisy? I didn't get the point here.
No, we didn't divide the documents here into sentences. We divide them into passages of fixed size. The problem here is that a document that is relevant doesn't mean that every passage in that document is relevant, right?
Right.
But in training data, we have no other option than assuming that all passages within the relevant document are relevant.
Oh, okay.
Okay.
Yes.
And that's the training data that we use. So many of them will actually be wrong.
Yeah.
They are right at the level of the document, but noisy at the level of passages.
So this is automatic labeling for the passages.
Exactly.
Yeah.
Translating from the relevance at the document level to the relevance at the passage level.
Okay.
Okay. Did we have this problem with BERT?
No, because we
Why
are
not?
trained, because we already trained on complete tweet or complete microblog.
Exactly. We didn't have this problem with BERT.
Yeah.